wanted to read a passage from one of my favorite books, The Cult of Statistical Significance, that talks about one of the logical fallacies in traditional hypothesis testing. And this is page 155. Suppose you are the sheriff arriving on the scene of the Oxbow incident. Let the hypothesis H be the character played by Anthony Quinn was hanged, as in the film of 1943 he was, and the given fact, the data, be that the character played by Anthony Quinn is dead. In general, the probability of death by hanging is very low. People are not hanged every day in significant numbers. If, on the contrary, the given fact, the data, is that Quinn was hanged, we repeat that we mean the character played by him, not dear Anthony. Then the probability of the hypothesis Quinn is dead is very high, say between 95 and 100%. The Fisher test can shed light on the probability that Quinn is dead, given that Quinn was hanged. What the Fisher test wants to know and claims to measure is the opposite, the probability that Quinn was hanged, given that Quinn is dead. In societies unlike that of Oxbow, in which hanging is exceedingly rare, this probability, as we've noted, is close to zero. In fact, even in 1885 Nevada, the probability Quinn was hanged, given that Quinn is dead, that is, the probability of the null hypothesis given the data, was low, radically lower anyway than a mistaken 5% philosophy would infer. In a non-hanging society, people die for many reasons other than hanging. People die from dehydration and cattle stampedes and bullet wounds. People die from cancer and flu and cardiac arrest, and therefore being dead is very weak evidence indeed that Quinn was hanged. Statistically speaking, the power of the test is not even defined. Dead is the datum, not the hypothesis. Being dead is consistent with the hypothesis that Quinn was hanged, to be sure, as the positivist rhetoric of the Fisherian argument emphasizes. But so what? A myriad of other hypotheses, very different from being hanged and emitted from Fisherian models of unknown power in arbitrarily emitted variables, such as catching pneumonia or breaking your neck in a fall from your horse, are also consistent with it being the fact of being dead. The Fisherian test neither falsifies nor confirms. In the film, incidentally, it was the lynch mob and not the sheriff that transposed hypothesis and data. They hung the wrong man. So the point being that when we conduct a hypothesis test, we're really only considering one state of the world and seeing how likely our data is to have been generated by that state. But we're disregarding all other possible states of the world. It might be the case that even if we rejected the null hypothesis, based on statistical significance, which is, another problem in itself, uh, we might say that the data was very unlikely to have occurred under the null hypothesis and reject the null hypothesis. But it still could be the case that the null hypothesis itself is still the most likely explanation to have generated the data. And so when we interpret these findings in any hypothesis test, we are reversing uh, the the order of our interpretation from the actual evidence that we had. And so we're trying to make claims about what state of the world is most likely to be true given our data, even though all of our evidence was based on how likely the data was given that state of the world. Um, we don't actually care about this specific data set or how likely this particular data was to have been generated. We want to make claims about what the state of the world actually is, meaning that we need to concern ourselves with uh, what state of the world is most likely as evidenced by this data. And the typical hypothesis test doesn't capture that. It doesn't tell the full story. And so this is a big reason why I think Bayesian thinking and modeling uh, is superior, because it actually encapsulates that entire distribution of possible null spaces, so to speak. Um, so I'll leave you with one more example of this coming from the paper "The Earth is Round, P less than 0.05" by Jacob Cohen. This is from 1994. When one tests the null hypothesis, one is finding the probability that the data could have arisen if the null were true. If that probability is small, then it can be concluded that if the null is true, then the data is unlikely. Now, what really is at issue, what is always the real issue, is the probability that the null is true given the data, the inverse probability. When one rejects the null, one wants to conclude that the null is unlikely, say p less than 0.01. The very reason the statistical test is done is to be able to reject the null because of its unlikelihood. But that is the posterior probability, available only through Bayes' theorem, for which one needs to know the distribution of the null space, the probability of the null hypothesis before the experiment, or the prior probability. Now, one does not normally know the probability of HO. Bayesian statisticians cope with this problem by positing a prior probability or distribution of probabilities, but an example from psychiatric diagnosis in which one knows the null distribution is illuminating. The incidence of schizophrenia in adults is about 2%. A proposed screening test is estimated to have at least 95% accuracy in making the positive diagnosis, that's sensitivity, and about 97% accuracy in declaring normality, or specificity. Formally stated, the probability of a normal test, given that the null is true, is about 97%, and the probability of schizophrenia, given the null is false, is greater than 95%. With a positive test for schizophrenia at hand, given the more than 95% assumed accuracy of the test, the probability of a positive test, given that the case is normal, is less than 5%, that is, significant at p less than 0.05. One would reject the hypothesis that the case is normal and conclude that the case has schizophrenia, as it happens mistakenly, but within the 5% alpha error. But that's not the point. The probability of the case being normal, given a positive test, that is, the probability of the null hypothesis given the data, is not what has just been discovered, however much it sounds like it, and however much it is wished to be. It is not true that the probability that the case is normal is less than 5%, nor is it even unlikely that this is a normal case. By a Bayesian maneuver, this inverse probability, the probability that the case is normal, given a positive test for schizophrenia, is about 60%.